Well, this video is for section 1.5 in the textbook, which starts on page 43. And so now we're revisiting the quadratic formula and quadratic equations with the possibility that we might have complex numbers as roots. So remember our standard form for a quadratic equation, ax squared plus bx plus c equals 0. So on page 43 in the textbook, and you can read through these yourselves, but I do want to talk about these examples that I show in the textbook in section 1.5. So the first equation that I bring up in the section is x squared minus 6x plus 3 equals 0. And if we run this through the quadratic formula, we come out with two solutions. X is approximately equal to 5.449 and 0.551. And if we graph this as a parabola, let's say we say y equals x squared minus 6x plus 3. Let's see, it'll look something like this. And these two x-intercepts are the roots. These x values are 0.551 and 5.449, because this is where y is equal to 0, is along the x-axis, right? All the positive y's are up here, all the negative y's are down there. So this is where y is equal to 0, so these are the x values that make y equal to 0. Okay. All right, now the next equation I bring up in this section is we change this 3 to a 9. And we can run this through the quadratic formula if we want to. It's also solvable by factoring, right? It's x minus 3 times x minus 3. So that'll give us what's called a repeated root. X equals 3 twice. So 3 is the only solution, but it has two factors of x minus 3. The graph of this is going to look something like this. So it just comes down and touches the x-axis at the value x equals 3, because 3 is the only x value that's going to make this y equal to 0. Okay, now the next step, the next equation I raise there is, I change that 9 to a 12, x squared minus 6x plus 12. Now, the effect that this has, you notice these parabolas are moving up, and so the shift from x squared minus 6x plus 9 to x squared minus 6x plus 12 has the effect of pushing everything up 3 places. And so this graph is going to look something like this. You've got a y-intercept over here of 12. But notice that there's no x values that are going to make the y be 0, right? Y is never 0. There's a minimum y value here that's a positive number. All the other y values are also positive. So let's run this through the quadratic formula and see what we get as a result here. So, if we put in 1 for A, negative 6 for B, and 12 for C. Now, something that might happen when you enter an equation like this, these values for A, B, and C, let me come around and show you what the calculator is saying here at this point. Okay, you can see it says error non-real answers. Okay, I'm not even sure why the calculator has this, so we want to quit out of this screen. So we hit second mode. That brings us back to this screen, and you can see it says error. The way to get around this is to go into the mode. You can see this mode button right here. If you just push that, then you'll get a screen that looks like this. And what we need to do is we need to come down here where it says real and a plus bi. So use the arrows. You can arrow down to real and then arrow over to the right to a plus bi and then push enter so that a plus bi gets highlighted, and then we can quit back out to the regular screen and run this through the quadratic again. All right, so a is 1, b is -6, and c is 12, and this time the calculator gives us these complex valued answers, 3 plus or minus 1.732i. Okay, so I'll go back up to the board and put our answers in there. So x is approximately 3 plus or minus 1.732i. Okay, so that's sort of the setup for this section 1.5. You can have quadratic equations that have 2 real valued answers, right? That's what we were looking at with this one. That was x squared minus 6x plus 3 equals 0. You can have quadratic equations that have 1 real valued answer if this is a perfect square. Okay, and then you've got quadratic equations that have complex valued answers. Okay, so let's take a look at some examples. The problems for this section, I believe, are over on page 49. Yep. So let's look at a couple problems here in this section. So make sure that your calculator is set up to be in a plus bi form so that you can run the quadratic formula program on these equations that have complex valued answers. So let's see, on page 49, we'll start off with problem 6. It's pretty straightforward. 5x minus 3x squared equals 17. So we want to put this in standard form so we can identify the values for a, b, and c. So let's see, we can move the 17 over to the left-hand side, and let's say we're in the habit of just putting the 17 there like that without changing anything around. There's nothing wrong with that, okay? This is not standard form, but it's not especially wrong, okay? The issue here is that a is not just whatever number comes first, okay? The a is the coefficient for the x squared term, and in this problem, that coefficient is -3. And the b is not just whatever number comes second. The b is the coefficient for the x term, what's often called the linear term. Okay, so here b is +5, and then the c is the constant term, which as it happens did come third. So our c is -17. So now we can take these values for a, b, and c, and we can run them through the quadratic formula. And that gives us solutions of 0.83 repeating, plus or minus, let's see, 2.230. 2.230i. Now these new calculators handle this very well. This repeating decimal, though, sometimes has issues. If you've got one of the older TI calculators, often this repeating decimal will hide some of the digits of that second number, of the complex part. So if you've got one of those calculators, let me show you how you can get around that. It's going to look different because my calculator doesn't have that problem, but let me just show you one way to go about fixing this. So if you've got one of the older calculators and you're having trouble seeing these digits over here, what you can do is if you look at the bottom here, right above that negative sign, it says ANS. So that's for the previous answer. So to get that, we hit the blue second button, and then we hit the negative sign, previous answer. All right, it's going to look like that. We hit enter. And there's our previous answer. Like I said, on my calculator it looks the same, but on the older calculators the benefit of this is that you can arrow over to the right, and that'll allow you to see the rest of these digits. Okay, so if you have one of those older calculators, you might run into that issue. Okay, so that's problem 6. Now, let's see here. Now, let's say you wanted to do something a little bit different. Let's say on this one, you wanted to move these over to this side. So you would add 3x squared and subtract 5x on both sides, and then you would get 0 equals 3x squared minus 5x plus 17. So here a is 3, b is negative 5, and c is positive 17. And you can run this through the quadratic, but it's going to give you exactly the same answers as we got for this one. Okay, I think I talked about this a little bit when in the section where we originally did the quadratic formula. Okay, it doesn't matter which side you collect everything on, it'll produce the same answers either way. Okay. All right, let's see here. Let's look at problem 10. Problem 10 is a little bit more involved. Okay, problem 10 starts out 2x minus 3 all squared equals 2x minus 7x squared. Okay, so first off we want to square this, which means that we need to multiply it by itself. And so this will be 4x squared. We'll get minus 6x and minus 6x to make minus 12x, plus 9 equals 2x minus 7x squared. So we'll add the 7x squared to both sides and subtract the 2x on both sides. So those cancel out and leave us with 0. Over here, we get 11x squared minus 14x plus 9. And then we can run this through the quadratic. Let's see what we get here. A is 11, B is negative 14, and C is equal to 9. And that gives us solutions of, let's see, this is a 0.63 repeating, plus or minus 0.643 I. So there's the complex answers for number 10. And then we'll look at problem 12. Let's see here, problem 12. We start out 3x minus 4 times x plus 2 equals 2x minus 5 times x plus 5. Okay, so we need to multiply these out and then collect our like terms. So we'll start out with 3x squared, and then let's see, a positive 6x minus 4x, so that'll be positive 2x minus 8. Over here, 2x squared, that'll be positive 10x minus 5x, so that'll leave us with positive 5x, and then minus 25. So I'm going to move all of this over to the left-hand side, subtract the 2x squared, subtract the 5x, and add the 25. So let's see what we get here. These all cancel out and leave us with 0. Over here, we're going to have 1x squared minus 3x and plus 17. And so now we'll run this through the quadratic. A is 1, B is negative 3, C is positive 17. Let's see here. And that gives us solutions of 1.5 plus or minus 1. Oh, I was thinking about the other problem, writing it before I even looked at it. 3.841 I. Okay. So that's just about it for this section. I am going to make a second video to show you something that's kind of just an extra to this topic. So the idea here is that, like I was showing you these graphs, remember if you look at x squared plus 6x, what was it, x squared minus 6x plus 3, right? If we graph that, then you can see the roots of the quadratic equation, x squared minus 6x plus 3 equals 0, end up being here and here. Now, with the complex answers, okay, remember the graph didn't intersect the x-axis at all, so we couldn't see the roots. Now, what's kind of interesting is that mathematicians and computer scientists have figured out a way to graph these equations for both real and complex numbers, okay? So remember, the complex numbers are two-dimensional, okay? You've got the real number line down here, and then you've got the complex, the multiples of I, going up the vertical axis like that, okay? And so these roots, 1.5 plus or minus 3.841I, they would be, let's see, 1.5 plus 3.841I and minus 3.841I. Okay, so in the second video, I'm going to show you the website. It doesn't have the axes, right? But you'll still be able to see where these roots are. At 1.5 plus or minus 3.841I. It's kind of an interesting thing. I'll revisit this when we get into chapter 2 a little bit, when we do a little bit more with complex roots. But it really is just sort of an extra thing. It's not something that you really need to worry about. But the graphs themselves are pretty interesting, and so I thought that might be a fun thing to do. So this is the end of the first half of chapter 1. Okay, so when we get into the next section, that's going to be a little bit different from these topics that we've been talking about in the first half, and then we'll get through that second half, and then I will start thinking about a take-home test. So we will see you then.